Systems of nonlinear equations. A system of nonlinear equations is two equations and two variables where at least one of the two equations is nonlinear. So for example, here we have x squared plus y squared equals 100. This is the equation of a circle. And then 3x minus y equals 10 is a linear equation. But because this is not a linear equation, this is considered to be a nonlinear system. Now, the solution to a nonlinear system is just simply the point where these graphs intersect. So we can see that if we graph the circle over here, and if we graph the line, they intersect at the point 6, 8, and they also intersect at the point 0, negative 10. Graphing, however, is a very inefficient method. Now, it's easy when you're looking at a graph, but how would you find these solutions without graphing? So one way to do this is to use the substitution method. So what I can do is take one of the two equations and solve for one of the two variables. The easiest equation to solve for one of the two variables is the second equation. Here I can solve for y by adding y to the right side and subtracting 10 from the left side, and that's going to give us 3x minus 10 is equal to y. Then I can take the expression 3x minus 10, and I can substitute it into the first equation, replacing y. So that first equation becomes x squared plus 3x minus 10 quantity squared is equal to 100. Then we're just going to multiply this out. So 3x minus 10, when you square it, you get 9x squared minus 60x plus 100. And this is still equal to 100. And now to solve it, let's combine like terms. We have 10x squared minus 60x. And then if we subtract 100 from both sides, we get 0. Next, I can factor out 10x, which will leave us with x minus 6. And we can see now that the two solutions here are x equals 0 and x equals 6. But again, solutions are not single values. Solutions are points because we are finding the points of intersection. So once I have x equals 0, I'm going to take that and plug it into my expression here that I substituted. Y is going to be 3 times 0 minus 10, which is negative 10. And that gives us 0, negative 10. And secondly, when x equals 6, y is going to be 3 times 6 minus 10, which is 18, minus 10, which is 8. And that will give us the other solution, 6, 8. And so you can see here are the 2 points of intersection, and we can solve for these without graphing. Another method for solving is the elimination method. Now, there's nothing wrong with the substitution method, and you can use the substitution method whenever you feel like using it. However, sometimes you can use the elimination method. And the way this method works is we're going to line up the like terms in the two equations, and we're going to try to eliminate one of the two variables. Now, in this case here, I can either eliminate the x's or I can eliminate the y's. I think I'll just eliminate the x's here. So here is our first equation and our second equation. And what I'm going to do is get the least common multiple of 3 and 5, which is 15. So let's multiply this first equation by 5. That's going to give us 15x squared. And then I'm going to multiply the second equation by negative 3. Oops, and we have to multiply both sides here. There we go. And that's going to give us negative 15x squared. So multiplying these out, the first equation becomes 15x squared plus 10y is equal to 130. The second equation is negative 15x squared minus 21y is equal to negative 9. And then when we add these together, we get negative 11y is equal to 121. Dividing by negative 11 will give us y equals negative 11. Now, once we know y equals negative 11, again, this is not a solution. We have to plug that in and then solve for x. So I'll plug it into the first equation. We get 3x squared plus 2 times negative 11 is 26. This is 3x squared is equal to 48. After you do a little math there, divide by 3, we get 16. And finally, x must be plus or minus 4. So we have two solutions. One solution is x equals 4, y equals negative 11. The other solution is x equals negative 4, y equals negative 11. And you can see, according to the graph, those are the 2 points of intersection. Now, in our final example, I will show you that you can solve systems by graphing, but it is a little more time consuming because graphing itself is just a little bit more time consuming. So if you're going to solve by graphing, of course, the first thing you have to do is you have to graph each equation. So that first equation, if I solve for y, I'm going to get y equals x squared minus 2. And then I would have to get some points. Now, we don't have to do it this way. We have other ways of graphing x squared minus 2. But if I plug in 0, I get negative 2. If I can plug in 1, I get negative 1. Negative 1 also gives us negative 1. And 2 will give us 2, and negative 2 will also give us 2. And so that first graph is going to be here, here, and here. And then on the other side, same thing. Maybe I'll just plug in a couple more points just to get a little better picture. If I plug in 3, I'm going to get 7, and negative 3 is also going to give us 7. So 3, 7 is here, negative 3, 7 is there, and there is that graph. Now the other graph, 2x minus y equals negative 1, is just a line. So this should be a little bit easier to graph. I will solve it for y, which is going to give us y equals 2x plus 1. And then when I come over here to graph it, we know we have a y-intercept at 1, and the slope is equal to 2. And when I graph that carefully, you can see that we get this line here, and there does appear to be 2 points of intersection. One point is the point 3, 7, and the other point is the point negative 1, negative 1, and those would be our solutions. So there's nothing wrong with this graphing method per se, but it is, in most cases, a little more time consuming. And the other thing you have to ask yourself is, what would you have done if when you were graphing, let's say you got one of your curves was like this, and your other curve was, say, like this, right? What would this point of intersection be, right? We would not really be able to tell for certain what that point would be because it's not on a corner. It's not on a whole number. So this is another kind of weakness of the graphing method. So primarily here, we should be really practicing our algebraic methods because they are precise. And that concludes this video lesson.